Okay, so Module 4. Module 4 is special. Okay, Module 4 is special, and it's special because we are not using Chapter 4 in the e-textbook that we have from McGraw-Hill. We're not using that chapter at all for Module 4. Instead, I have for you, I'll put this back up. What I have for you a PDF of a chapter out of a different book. It's actually the book I used to teach out of, okay? And we can use this, it's like legal, if you would, copyright wise, because this book is no longer in print. So it's just a PDF of that. Now it's chapter 4 out of that. So I have provided this PDF right here in Module 4. So if you click on that, it's chapter 4 out of this. So everything we do in terms of the content that we're going to be talking about, all of the references go back to this PDF. All of the homework problems come out of this PDF. So nothing is being done out of the book online, which means there's no Module 4 Connect assignment. Okay, so you don't have to worry about that. All right, so everything is out of this PDF and the notes that I have here. The other thing that I have for you guys, okay, are these guided, I'm calling them guided notes. So if I go back in here, here's that PDF for the chapter. So it says chapter 4 using this handout, okay, not the book. Then I've got these guided notes here, okay? And if we click here, if you're virtual and you've had a chance to print them off, great. If not, just take notes as we go along. But I'm going to have some fill in the blanks. We're going to reference some feature or figures, but then we're also going to be doing some examples out of here too. Okay, so so I've kind of tried to organize it a little bit for you guys. And then this would be, for those who are filling it out on here, this would be your practice problems. Okay, this would be your practice problem. So you don't have to do separate notes on the side. Okay, but I have these notes here for you. So if you're in the class, there is the handouts up in the front here. If you're virtual, then you can either follow along notes wise, or you can print this off and work through this. So that's what I'm going to be using underneath my camera. Okay, so those two things are different than what we've had in the past. And I'm kind of testing out the guided notes thing. Suggestion somebody gave, and I thought they looked kind of good, so I thought I'd adapt it here. We're doing a lot of examples. Okay, so the guided notes, if you follow along and you do them along with me here, you'll have room enough to do those examples right in the handout. Okay, but otherwise you'll have to do them on the side. So you won't have to, do two separate. And then we have some application problems as well. And again, like I said, no Connect for this module because we're going out of the McGraw-Hill book. Okay. All right, so let's start looking at our guided notes. I'm going to go underneath my camera here and scooch this around. And again, chapter PDF, and then these are my guided notes. The guided notes, there's 22 pages, which is like crazy, but it's a lot of good stuff. That's what that can tell you. Okay. So at the beginning here, chapter 4 is about determining the resultant of non-concurrent force systems. So chapter 2, this sounds really familiar to us, but there's one little part that's different. So chapter 2 was resultant of concurrent force systems. Concurrent force systems where the forces shared a common application point, or if we extended them, they shared an intersection. Lex, there's a handout here for you that we're going to work through. So you'll notice that here it says resultant of non-concurrent force systems. So what that means is they're not going to have that common point. So the problems are going to look a little different. Okay, there's not going to be those intersections that we were looking for before. So so one of the concepts at the beginning here is it's called the principle of transmissibility. We've touched on this actually. We touched on this when we looked at that block that was on an inclined surface. Okay, and what the principle of transmissibility says for us is that it states that a force can be moved along its line of action. That's what you want to put here. It can be moved along its line of action. And it will still have the same net effect on the body. Okay, so what does this mean? So let's go to our chapter. And at the bottom of the very first page here, figure 4.1, we have this force F, okay? Force F is on this blob or this, like just this object, this body, okay? And the body is just this, you know, this oval that we see here. So in the first illustration, we'll notice that force F is applied and starts at point A, okay? And you'll see this dotted line that goes through here. So if we draw a line extending, you know, up and to the right and down and to the left to infinity, this is the line of action, or if we move that along, that's the line of action of that force. Now, as the principle of transmissibility says, if we move that force anywhere along its line of action, it's still going to have the same net effect on the body. So right here, the effect on the body that force F has on it, how would you describe that? What would be the movement if this wasn't like locked down? What would be the movement of that rigid body? Which way would it go? Up and to the right, right. So this is at A, it would want to have the tendency to move up and to the right because that's the way the force is being applied. Okay. So let's move that along that line of action, but up to point B. Okay. Notice here that we have that same force, but now it's along and it's being applied at point B. Will it have that same net effect on the body moving up and to the right? Yeah. Yeah. Whether I pull on it up here, or even if I push on it from the bottom, it's still going to want to go up and to the right. So the principle of transmissibility says I can move that line anywhere along its line of action, that force anywhere along its line of action, and I'm still going to have the same net effect on the body. As we turn the page, there's another illustration at the top, which goes really over that very same thing. In this part A of this figure, we're pulling in two different directions on points A and B. Extending the line of action of B back and applying it at force A or at point A, notice that you're still going to have the same net effect. It's still going to want to equal out and just stay where it's at, assuming that the forces are the same magnitude based on the length here. Okay. So, so that's principle of transmissibility. Sounds so smart, but just means we can move a force along the line of action. It's going to have the same net effect on the body. Okay. Now, the next thing we're going to talk about, which is really like the big deal in this chapter. Sorry. The big deal in this chapter is introducing the idea of moments. There's handouts right here. Is this idea, no, over there. I put it up here because I thought Chris was going to be here, but he's virtual today, so that's okay. Oh, I'll turn my camera on. I know, that's okay. Just meet with me after class. If you were late coming to our lecture tonight, I was talking about next week, Monday, when we have class again, it is an in-person meeting because that's our unit assessment. So if you missed any of that talk beforehand about the unit assessment, make sure you stick around after class and ask me about the details because I want to make sure everybody's on the same page. All right, so 4.2, moment of a force. This is the new concept here that we're going to continue to apply. And a moment of the force is going to be the tendency of a force to produce a rotation about an axis or a point. Moments produce rotations. So the moment of a force about an axis is defined as the product of the force and the perpendicular distance. So perpendicular is going to be what goes in here. From the line of action of the force to the axis. Okay. Now, the equation for a moment is going to be capital M. This is moment. This is a symbol for moment. The O here is just the reference to a point. So it could be an origin O, it could be A, it could be B, it could be C, whatever point that we're referencing a moment to, and it'll make more sense when we start doing more stuff. Capital F is the magnitude of the force. So we would expect those units to be in pounds, newtons, those types of things. I'll put that in back of this. So this is going to be, I'm going to say pounds, newtons, kips, Any units for force would be applicable. Units for mass would not be, so a kilogram will not go in there, okay? And then our last is distance. So this is going to be inches, feet, meters, those types of things, okay? So a moment, very simple, force, the magnitude of the force, times the distance, the perpendicular distance back to the point that we're summing our moments around, okay? So the units for moment, English units for moment, we're taking force and we're multiplying it by distance. That means that our units are going to be force times distance, or pound inches, pound feet, Newton meters. Notice what I'm not doing. I'm not saying newtons per meter. I'm not saying pounds per foot, because the equation is force times distance, right? Force times distance. So units here are going to be pounds times inches, pounds times feet, kips times feet or inches, anything that is force times distance. So English units. Now remember, a kip is 1,000 pounds, a kilopound basically. So the metric units are going to be newtons times meters, newtons times centimeters, kilonewtons times meters, and you get the idea, right? Multiplied by, not divided. Questions so far? Okay. We're on the page. So we're going to turn over to page 2. Theorem of moments. Theorem of moments. I'm going to actually go down here. It states that the moment of a force about a point is equal to the sum of the moments of the components of that force about that very same point. Okay. Now, as we had stated earlier, we are going to be finding the perpendicular distance of a force from a point that we're interested in knowing what is the tendency of that force to rotate about. So a very classic example is a wrench, okay? A wrench is intentionally going to rotate about the center of the bolt head here, right? We put the wrench on there, and then we're going to push with a force along that handle to tighten it or loosen it up, right? Now, there's one reason why I don't like this example, because when we talk about wrenching and tightening with a wrench, what is the term we usually say? Torque. And you're going to notice that if you know the equation for torque is force times distance as well. And yes, it is related, but it's not the same. A moment is going to be the tendency of a force to cause a rotation on an element that is not intended to rotate. So when we're talking in statics, for instance, like a structure, a beam, a block, anything, it's got a force on it. A lot of times we're looking at actually supporting those forces, not intentionally rotating them. So we call them moments. We will talk in, I'm pretty sure it's in strength of materials. You will be talking about torsion, okay? And that's where we're going to be talking about torque, okay? An intentional rotation about a center, if you would, okay? Or sometimes we talk about it in terms of torsional shear stress, where we have something that's torquing, and then we have to know how much stress it's creating so that we can size material appropriately. But this is not torque. So the units are not foot-pounds or inch-pounds. We say pound inches, pound feet, force first, and then the distance second, okay? Might feel a little ticky-tack, but it is distinctly different, okay? Moments and torques are different. If they were the same, we would be calling them torques. They're not, okay? They're not. So I just want to make sure that we know and understand that. Now, as we're looking at this example in terms of moment, yes, torque is what we usually say, but don't, but don't. As we had stated earlier, the moment is going to be the product or the multiplication of the force times the perpendicular distance. So if I look here at point F and where it's applied, it's applied at A. If I would take the distance from the origin or the center of rotation, and I would measure this distance right here, I cannot use that distance. That is not my distance. Can you tell me why? Go ahead. Correct. It's not perpendicular. The angle is actually larger to the force. If the force was standing up vertical, then I could take it, but it's not. So what I need to do then, take that away from there. I don't want it. I don't want that distance. That's not the one we want. To get a perpendicular distance, I would have to move this along its line of action. What is that called? The principle of what? Transmissibility. It sounds so smart. So when you go home, or if you're at home, and someone's like, what are you learning in school? You say, I'm learning about the principle of transmissibility. Mean anything to you? And we're like, no. Yeah, I know. It's pretty smart. Do that. Right. The stuff that you're learning is smart stuff. So yeah, principle of transmissibility. So I'm going to move that force along its line of action. And do you see how I would then find a distance perpendicular? This would be my distance. Perpendicular to the line of action of that force. Okay. If I leave it in that orientation. Now, knowing what we know about components, go over here. You could also break that force into its components. And instead of using the magnitude of the full force, we would actually use the magnitude of the y component that now makes a perpendicular. And now we would use a distance here. That would be perpendicular, but we'd use the y component, not the full magnitude of the force. Does that make sense to everybody? Okay. So as you can imagine, we're probably going to do a lot over here. Okay. We're going to be breaking things into components that aren't vertical or horizontal. Okay. So let's fill in our stuff at the top here. Okay. So we looked at that example. So when we break forces into X and Y components, you'll notice that the Y, the Fy has a blank, a perpendicular distance from O, that origin. So it's referencing it's referencing this illustration at the bottom of that page 65. Okay. Now, again, for those who are coming late, we are not using the chapter out of the book. We are using the PDF in the learning plan, and that's what I have underneath here. So it does look different. So the homework problems also are coming out of this PDF. All right. Fx passes through the origin, so it does not cause a rotation. Let's look at that one. Okay. So that Fx component, if I push this along its line of action, do you see how there's no distance? It goes right through the point. So there can't be a rotation. There can't be a moment calculation because my distance would be times 0, right? Okay. So it has to be a perpendicular distance offset that causes rotation about that point. If I push on X, it's going to push on my point. See that? Okay. So we already discussed the theorem of moments, but let's restate it. It states that the moment of a force about a point is equal to the sum of the moments. So again, there can be more than one force causing rotation about a point, and many times there are, of the components of the force about that same point. So to write this, we are going to use the summation symbol, okay? Just like we did for some of the forces. We're going to say capital M. And this little, I'm going to use 0 for right now. It's just going to be the reference to the point that we're going to be summing around. So it's a subscript, right? Is that sub is down? What's the up one? Superscript. Thank you. Is going to be equal to, right? Now leave a little bit of room. You're going to put a parentheses, and it's going to be F1 times D1. So the first, the force and its corresponding perpendicular distance. And out in front, you're going to put a plus minus because we're going to determine that based on the direction of rotation. We'll talk about that in a little bit. And then we're going to continue on plus minus F2 times D2. We're going to continue plus minus F3 times D3. And then just kind of put some dots behind that because it's going to depend on how many forces and perpendicular distances are causing rotation about the point, in this case, O, that we're going about. So this means the sum of, just like it did for forces. Now this is going to mean the sum of the moments about point, and then whatever it would be. You can have an A there, a B there, an X, a Y, whatever. Okay, it can be about an axis. And then the F is going to be the force, the D, corresponding distance. So we multiply those two together inside of the parentheses. And then the plus minus for each one of these is going to be the direction of rotation. Okay, direction of rotation. Now, to get the direction of rotation, we need to add to our standard convention. So we're going to have a new convention. So we're going to draw a new convention. Parts of it are going to be the same. So this part is going to be the same. So everything in the X direction is going to be positive, or to the right is going to be positive. Up in the Y direction is going to be positive, and anything that is rotating counterclockwise is also going to be positive. So we're adding that rotation onto our convention. That's the new convention, and that's what we're going to be using from here on out for every single problem. Okay. All right. Did everybody get the stuff that's up here? Any questions at all? So perpendicular for the first one, rotation. Some of the moments around a point, plus or minus force times distance, however many there are. And then our new convention. Yes.
Just a theory question. Is there ever a time where you use f of x to calculate it?
No. Oh, you mean like when you say f of x, the x component of a force? Oh, yeah, we will. In that particular case, it just was along that line of action. So, so as we do some examples here, yes, any one of those components, and we will break forces that aren't on the x and y component into, or on the x and y axis into their components, because then we've got like easy perpendiculars. We'll find it's going to be easier. All right, let's do an example. So again, we're working out of the PDF. Okay, so this was page 65 that we were just looking at. We're going to turn the page. Page 66 down at the bottom is the start of example 4.1 right here. Okay, bottom of page 66 in the PDF, not your McGraw-Hill book. Okay, so you'll notice here that we've got space to start this. Let's look at the problem statement. It says here, find the moment of the 120-pound force at C, and we want to find the moments about points A, B, C, and D for that rigid body. Okay, so how we're going to start this is we're going to draw a free body diagram of that length, that bar. I'm going to zoom out a little bit. Okay, we're going to go down underneath here. And a free body diagram is going to be a simplified version of, so pretty much I'm not going to draw any thickness. I'm just going to draw a line. Okay. Oh, I've got room on the next page. Good. So I'm going to I like making my free body diagrams nice and big, as you know. Okay. Now I want to duplicate what I have there. So I've got A, then 4 feet B, then 2 to C, then 2 to D. So here's going to be my A, here's going to be my B, and then here's going to be my C and my D. So A, B, C, and D. Okay. Now between A and B is 4 feet, between B and C is 2 feet, and then 2 feet. Right? Yeah. And you can use the symbols for the units, is fine. And now I'm going to draw at C that force of 120 pounds. Now, there's no angle to it. So our assumption is that it is 90 degrees because it's being shown vertical. Okay. So there's my free body diagram. I've got it identified or represented by just a straight line. I've got my points labeled, proportionately have my distances labeled as well. I know I did not scale those, but you know, it's a little bigger gap here for the 4 than there is for the 2s. I have my force with an arrowhead. With an arrowhead, remember, from here on out, we're gonna have a lot of forces in static, strength, and materials. They all need arrowheads. So make sure you're putting those on. And then labeled as 120 pounds, units need to be in there. So that was draw the free body diagram, add all labels. The next thing is include the new convention. So in the upper right-hand corner of every problem you do, not homework assignments, not once for the whole homework assignment. No, no, no. Every new problem, it gets a new convention. It's going to be the same convention every time, every time. So we're going to put that up there. And we want to find now the moment of the 120-pound force that's at C. We want to take the moment about points A, B, C, and D. Okay, so we've got plenty of room on the next page here. So I'm going to zoom out, bring this back, and I'm going to put that up there. Okay. Now, I want to find the moment about point A. So what I'm going to do is I'm going to sum my moment about point A. That's how I'm going to say, this is what I'm going to do. I'm going to sum my moment about point A. Summation symbol, capital M, sub A. Do not forget the summation symbol. Do not forget the M, and don't forget the A. Any one of those by themselves is not this, okay? It's going to be equal to. Okay, now I'm going to start my parentheses. Remember, my moments are always force times distance. We're going to put both of them inside the parentheses. Okay, and it'll make sense, more sense why we do that. So I'm going to look here. I'm going to say, okay, I'm going to put my finger on A. That's how we do this. Finger on A, because I'm summing my moment around A. And I'm going to find the force. And I'm going to put my finger on that force. And I'm going to push in the direction of that force. And I'm going to look, did I rotate my paper? I did. Okay. So that means that it's causing a moment, a tendency to rotate. Here's my center of rotation and here's my force. Yes, it's going to rotate. Okay. So in the first part of this, I'm going to write the magnitude of the force. So this is going to be 120, put your units with it, pounds. Okay. Multiplied by perpendicular distance. So I like to think of this, and I don't know, sometimes it seems like it makes more sense, and maybe it'll make more sense to you. So if I look at the center of rotation for a circle, for instance, okay, and I think of that as my point that I'm summing around. And if I go out to the side here, okay, and I draw a force that's tangent to the outside, but it's perpendicular to the radius, do you see how we're kind of doing the same thing there? So I want to know what is the radius, if you would, of the rotation that's being created. Okay. And that's what I'm trying to find here. So from point A to 120, do you see how 4 plus 2 would be my perpendicular distance or my radius of the rotation? Okay. So that's going to be 6 feet, or you could put FT. Now I'm not done because I need to put a sign out front. Remember up here where we had the sign out front, plus or minus. That sign out front, what do you think we're gonna relate that to? Get your convention. What haven't we used yet? The rotation, right? The rotation. So if this is rotating in a counterclockwise direction, it's going to be positive. If it's rotating in a clockwise direction, I'm going to put negative out front. So as we look here, I'm going to put my finger on A again. I'm going to rotate. Which way is it rotating? Clockwise or counterclockwise? Counterclockwise. So that means out front, I'm going to put a positive. Positive. This is a counterclockwise direction of the moment. Now, it is very important that you put this in brackets because the moment is the product of the force times the distance. I can't emphasize that enough. If you don't put this in brackets and you put a positive in front of the force, it looks like you're making the force positive, and it is going up. But we can have, and we're going to find cases where we have positive forces creating negative moments, causing a negative rotation. Or we could have a negative force, directed force, causing a positive or a counterclockwise direction of rotation. Okay? So this is always inside of our parentheses, force times distance, and then outside, we are labeling the rotation of the moment that's generated. Okay? All right, questions so far? As we look then past the 120, there are no other forces. So in this case, to sum our moments, it's just one moment or one force, okay? So I'm going to say sum my moment around A is equal to, I'm going to put the positive out front and I'm going to take 120 times 6. What's that number? 720. 720. And what are my units? Pound feet, exactly. LB, FT. Usually in my final units, I'll put the LB. I tend to not in the work, only because it tends to look like a 1, and I've made the mistake before of putting a 1 in as I'm doing things. All right, now you'll notice that the positive out front, what does that tell me? It tells me the direction of rotation. So even in this form, when I have it multiplied out, the positive out front says that moment around A is going to go counterclockwise. Okay. All right, let's do the same thing for B. Sum my moments around point B is equal to. So now we're going to move our finger down to point B, and we're going to do that same thing. We're going to push in the direction of that force. It's causing rotation still, okay? So we're going to start our parentheses, 120 pounds times perpendicular distance from B. 2 feet this time, right? So 2 feet. Okay, and then I'm going to close my parentheses. Now out front, I need to show a sign. The sign is going to be related to the direction of rotation. So it's going to be counterclockwise again. I'm up against my camera up there, so I can't always rotate. So I'm going to put positive out front. So the summation of the moments around B is going to be equal to 240 pound feet, and put a plus outside. You can do a positive assumed, that's totally fine too. But no, that means something, okay? The last one, or no, the next one, sum the moments around C, okay? Let's put our finger on C. Let's push in the direction of that 120. Is it rotating? No. Do we have a moment at all? No. So we can just say sum the moment around C equal to 0. There's no rotation of that moment or of that force about that. It has to be offset, right? There has to be a radius, if you would, there. All right, and then our last one. Our last one is D. We're going to put our finger now on this side, okay? We're going to push in the direction of the 120 pound force. It is causing a rotation. So I'm going to go back over here. Summation, put a box around that one. Summation of the moments around D is equal to, start my parentheses, leave a gap for your plus or minus. This is going to be 120 pounds times perpendicular distance. From D back to C is 2 feet, right? So 2 feet again. Sign out front. Negative, because it's going in a clockwise direction. We have a positively directed force causing a negatively directed moment, right? Okay, so again, that sign out front is for the rotation. So the sum of the moments around point D is negative 240 pound feet. So the negative means it's rotating in a clockwise direction. All right, any questions? This is a concept, it isn't hard. It isn't hard, but it takes a little bit because now we're thinking of 3 things at once. We're thinking of forces going up, down, left, right. And now we're also thinking of moments, okay? So we have to know kind of when we're in moment mode and when we're in force mode. Because when we're in force mode, we just look at the direction, right? And we give it a positive, negative. But moment mode, we can't just look at the force. We've got to look at the rotation it creates based on its direction and any offset, Okay, so, so there's a little bit more there. It's not just based on the force. Good, 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 good. Let's look at our next example here. Our next example is on page, it's number 4.2, and it's on page 67. So we are going to turn the page. Okay. And, oh, at the top of the page was what we had just done, the answers for that. But now we're going to have a different problem to do. Okay, now we're gonna have a different problem to do. So this one says we want to determine the moment about point C, just right here, due to force F, okay? And the magnitude of force F is 100 newtons, and it's applied down here at the bottom of the bracket, okay? So right now we're gonna actually solve this very same problem two ways. We're gonna solve it once using and determining the perpendicular distance from point C to the line of action of F. Okay, so you can see over here, we're going to extend that line back. We're going to kind of do some trig figuring, but we want to ultimately know what is that perpendicular distance to that force. Okay, and we'll figure that out. Then the other way that we're going to solve this, we're going to get a number for the moment. The other way that we're going to solve this is at the top of the next page, we're going to break that force into its components. And we're going to see how by using the X and Y components, we now can also obtain the very same answer for the total moment around C. Okay. And then there is a solution 3, but we're not going to do that. We're just going to do these first two, and that's plenty. Okay. So first things first, we need to draw our free body diagram. So the space that we have available is the bottom here, but then we also have page 4 and we have page 5. For both parts. So I'm actually going to start up at the top of page 4, because that way I can, rather than trying to flip back and forth, this will be better. So I want to show my diagram right here on the left-hand side, and I'm going to simplify it. And I'm going to start it here. And I'm going to go down. Okay. And this is going to be my point C. This is going to be B, and this is going to be A. The distance from C to B is 8 meters. The distance from A to B is 0.6 meters. I'm sorry, 0.8 and 0.6. I'm going to right away put my convention in the upper right-hand corner with my rotation, my new convention, so I don't forget, always at the start of any problem, every problem. And then down here, let me see here. It's a 60-degree angle from vertical. So I am going to draw a vertical line here. And oh, I've been on a kick where I'm doing this. You don't have to do this. So this would be 90, 60. Here it is. And I'm going to show that force F at a 60-degree angle from vertical. Okay. And I think it was 100. Yep. 100 newtons. F is equal to 100 newtons. All right. So we want to obtain that perpendicular distance, right? Right here. So I'm going to kind of draw this right here. Perpendicular distance. And we want to know what is D, right? Now, to do that, if we extend, and I'm going to do it in dotted and dashed lines, extend this line horizontally, and we extend this one along its line of action. Do you see how we have a right triangle right here? See that? See the right triangle? Oh, got a highlighter. So I know there's quite a few lines here. So we look, we've got a right triangle from here, here to there, right? Now, if I look at the geometry that I have, this angle opposite would be 60 degrees, right? I have another right triangle right here. So what is this angle right here? What is that angle? You can do it in the chat too, virtually if you want. 30 degrees, yes, 30 degrees right there. And that's also then 30 degrees for the big triangle, right? For the big one. Now, as I look here, my 30 degrees, if I go all the way across, that's the side opposite, right, is D. And I could probably find the hypotenuse, right? The hypotenuse I can get by adding 0.8 plus this out here. There in the book, they call this point E. So BE is the leg of this right triangle, right? And if I have 30 degrees and I know the side opposite is 0.6 and I want to find the other leg, what trig function would I be interested in using? No, not sine. Sine needs a hypotenuse. We're not on the hypotenuse is over here for this triangle. We need a leg. Tangent, absolutely. So we look here, we can say tan of 30 degrees is going to be equal to the side opposite, which is 0.6 meters, divided by BE, right? BE. So to solve for BE, I'm going to multiply this up and bring my tangent 30 down. So I'm just going to rearrange this. BE is equal to 0.6 meters divided by tan 30. Do you guys see how I did that? Right? Any questions on that at all? Make sense? So now I can solve for BE. BE is going to be 0.6 divided by 30 sine, or tan 30, sorry. So BE, this part, this length right here, is 1.0392 meters, okay? So now the entire hypotenuse then, this right here, my hypotenuse, is going to be equal to that plus 0.8, right? So that's going to be 1.8392 meters. Now we can calculate D, right? We have the 30. D is the side opposite. And now I have the hypotenuse. Make sense? So if I say sine of 30 degrees is going to be equal to D, oopsie, sorry, for those who are virtual, D divided by my full hypotenuse of 1.8392 meters. My unknown is D, so I'm going to multiply this up. So I'm going to take this times this, and D is going to be equal to 30 sine times, should get 0.9196 meters. Really not a final answer. I shouldn't have boxed it. I'm not done yet. Am I? What? Yep, sine function, because we've got 30 degrees here. Side opposite is D over the hypotenuse, which is adding the 0.8 and the 1.0392. Okay, so that's my distance. I need to sum my moment about point C, don't I? So now that I have this distance, okay, so this is kind of like step number 1 for this one, right? Step number 2 now is going to be summing my moment around point C is equal to, and it's going to be my 100 Newton force times my perpendicular distance of 0.9196 meters. Now, before I start calculating anything, what do I need to add here? I'm missing something. I'm missing the sign. So I need to go up here. I need to put my finger on C, and I'm going to pull in the direction of the 100 Newton force. And which way is it going? Positive or negative? It's going negative. Yes, 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 yes. So it's going clockwise, so negative out front. So the sum of the moments around C is going to be equal to, I multiply that by 100, so negative 91, a little bit of room there, negative 91.96 newtons times meters. Force times distance units, okay? Not newtons per meter. All right, that's the first part of this. That's the first way to do that problem. Okay. The second way we're going to do this very same problem is instead of using, if you would, trig, which is fine. I mean, I don't think it's not hard and not bad, but let's break this force into its components and then use the distances that were given. Okay. So on page 5, there's a blank page again. We will set this one up in that way. Try to keep these in order if I can. Okay, so blank piece of paper. I'm going to start at the top here, and we're going to redraw that very same illustration at the beginning. Okay, so 0.8 in this direction, 0.6 going down. This is C, this is B, this is A. 0.6 meters, 0.8 meters. Okay, 90-degree angle here, assumed. And then from vertical, I'm gonna do a horizontal as well, because we're gonna have X and Y component, right? So I'm gonna draw this like that. And I'm gonna be 60. This is my force here. F is equal to 100 newtons. Okay. This was 60 degrees, right? 60 degrees. So we want to break this into its X and Y components, X and Y. And along the X and Y axes, we're going to draw. Now they're calling this F, so we'll call this FY, okay? And it's going to be pointing down. And then FX is going to be pointing to the left. This is FX. Now, because we know the 60 degrees and we know the magnitude of the force, do you see how we can calculate the actual magnitudes of FX and FY, right? Go ahead and do that. Go ahead and do that. So step 1 is our diagram. Step 2 is going to be components. Okay. Watch your placement of your angle. I should hold a couple more. 6.025. I think 3-4 decimal places is reasonable. Might be a little overkill, but that's okay. So you should get for FX 86.6025 newtons, holding those extra decimal places inside of the problem. We'll round at the end. And then our FY is going to be 50. Notice that both are down, they're in their negative, if you would, direction. So the X is going to the left and the Y is going down. No negatives for the variables here. The negative would be just shown in the arrow pointing down, the arrow pointing left. Don't put negatives, just calculate for their absolute values. And then we'll use our, directions later on to get our signs. Okay, any questions so far? This is like all familiar. This is nothing's new here. Now what we want to do is we want to determine the moment around point C, okay? So step number 3 then, we're gonna sum our moment about point C. Okay, sum the moment about point C. So we're gonna look, put our finger at C. And I'm gonna pull in the direction of FX. Pull in the direction of FX. You're gonna notice that there is a rotation here. Now, I didn't put the convention here, but I'm gonna add it because this is still part of the same problem we started earlier. So you don't have to do it again, but this is our convention. So that's our convention. Which way am I rotating? Clockwise or counterclockwise? Clockwise. So out front, I'm gonna do what? It's gonna be a negative, negative value out front, right? For this first moment. Now, in the parentheses, what's the magnitude of the force that I'm gonna write right here? It's the 86, right? 86.6. Nope. I'll get there, but this one's causing rotation, right? That's the one we're pulling in. It's causing rotation. So 86.6025 newtons is my force causing rotation times perpendicular distance. Move this one along its line of action a little bit. Okay, move it forward. And now here we can apply this force over here. And what's its perpendicular distance back to C? Right there. And what is that? What's that magnitude of that perpendicular distance to C? 0.6 meters. Okay, so the force is the 86.6 and the distance is the 0.6 meters. So moving this along its line of action, perpendicular distance back to C is going to be 0.6 meters. Now let's check the Y. Okay, let's check the Y. If I put my finger on C and I pull in the direction of Y, it also causes a rotation. It does. So I'm going to start my parentheses with the magnitude of my Y, which is 50 newtons, right? So I'm going to put Fx above this one and then Fy above that one. Now, perpendicular distance for this one. This one's down here and C is up here. So we can back it up along its line of action. Do you see that? And if I would simulate it right here, it's going to have the same effect. What is its perpendicular distance? 0.8. And put the meters in there. Now, the last thing we need to do is add the sign. So if I pull in the direction, whether it's down here or up on top, what direction am I rotating? Clockwise again, right? So negative out front. So now if I sum my moments about C equal to, I know it's going to be negative, right? Because I'm adding two negative values. So 86, 6, 9. And I'm getting a negative 91.97 newtons times meters. And if I remember correctly, on our previous problem, we had negative 91.96 Newton meters. Okay. So either way, we get the very same answer. We get the very same answer, whether we do it with the perpendicular distance, solution 1, or if we break it into its components and use the solution 2. Okay. Questions? Okay. All right. Turn the page. Let's do another example. We're going to go to example 4.3. This is on page 69 in our PDF, not in our book, in our PDF. So 4.2. Here. 4.2 is at the top here of page 69. And here we have a truss. Okay, here we have a truss. And it says we want to determine the moment of the three forces that act on the truss as shown about points A and point C. Okay, so first things first, we have to draw our truss out. And you're going to notice that we have one of the forces which acts along the line of action of one of the members, we're gonna be breaking it into its components, okay? So, so let's get a nice diagram and represent that force and make it large enough so that we can put the right labels and it makes sense of it. So before I start, I'm gonna put my convention in place, okay? How are my triangles so perfect, Alea? I don't know. I'm eyeballing it, but I'm using straight edges, but yeah, I don't know. They don't always come out perfect, believe me. It's kind of lucky. I'm not gonna lie though, when I started doing this kind of working in the program that I went through, we didn't have really computers yet. It was that transition from boards to CAD, and I was always kind of hoping I'd get to do this for a living, but I never got to. That's okay. Okay, so as we're here, got everything identified. I want to start by focusing up here on F1. F1 is our force that's at an angle. So first things first, we'll determine the components there. Now this is going to have an X and a Y component. And what I want you to do is I want you to kind of say to yourself the direction of F1. It's going down and to the right. So sometimes students will get a little balled up on which way do I show my vector for the X and the Y. Talk it out. It's going down and to the right. That means that my Y has to go down then. Okay. So I'm going to show the arrowhead right here. So this is going to be F1Y. And then my X has to go to the right. Okay. F1X. Does that make sense to everybody? So make sure you have those going in the correct direction to represent the down and to the right direction of F1. Now, the angle, you'll notice that theta is here. So as we look, this is along that same line of action. So this would be the same theta as well. So if we look down in here, we can determine theta by using the side opposite and the adjacent or the tangent function. And I'm going to do that over on the side here just to ensure I've got enough room down below. So I'm going to say tan theta is going to be equal to 5 feet divided by 4 feet. Again, side opposite over adjacent. This is feet. Cancel out feet. So my theta is going to be 5 divided by 4 Second function tan. It's going to be 51.34 degrees. Okay. So that's going to be the angle then that we're going to use to calculate the two components. So go ahead. Step number 1 was our free body diagram. Step number 2 is going to be our components. And there's only the two components that we have to solve for. So I'll kind of push this up here. Our angle's in its standard location. So we can say F1x is going to be equal to the cosine of 51.34 times 10 kips. Okay. So my F1x gonna be 6.247 kips. And then there's a 0 at the end. My y component is going to be the sine of 51.34 degrees times 10 kips. $7.8087 kips. Okay. All right, so now we have everything set up so that we're ready to sum our moments around the 2 points that they're asking for. Oh, no, I'm not. I'm missing a force. I just noticed coming down here, I forgot my force at F. I'm going to sneak it in here. This is F, and that's F2 is equal to 8 kips. Okay, sorry about that. You probably remembered yours. I didn't see mine. I forgot it. Now we're ready to sum our moments around A and D. Okay. Zoom out just a little bit. So step number 3, we're going to sum our moments around, we'll start with A. Okay, we'll start with A. So that means we're going to put our finger on A. And I'm just going to start with the closest force here, which is at F. So if I pull in the direction of F, notice that it rotates. The magnitude of that force is 8 kips, units in all phases of the problem, so included here, times perpendicular distance, 4 feet. Okay. And then as I put my finger on A and I rotate in that direction, it's going to go clockwise, which is a negative rotation out front. So I'm just going to put clockwise. You don't have to put clockwise on yours. I'm just trying to put that in there as a note. Our next one, A, I'm going to pull in the direction of that 5 kips. Does that cause rotation? No. And it makes sense. If I move it along its line of action, it's going to go right through that point. So I don't even include it. I don't say F3 times 0. I just don't even put it in. It's not causing any rotation, so it doesn't need to be included in my moment equation. Finger back on A, and now I am going to pull in the direction of my F1x. That is causing a rotation. So my F1x is 6.247 kips. That's its magnitude, times perpendicular distance. If I push this back along its line of action and I go straight up to it, do you see how that's 5 feet? So if I go here, here's 5 feet perpendicular distance. Okay. And now direction. Finger on A, push in the direction of F1x. It's going to go clockwise, so that'll be negative out front. So that's another clockwise direction. So 6.247 kips times 5 feet for that one. All right, I've got one more force. I've got my Fy. My Fy, if I pull in that direction, it's causing a rotation. So I'm going to start by putting the magnitude, 7.8087 kips, okay, times perpendicular distance. This one is along, if I push it along its line of action, do you see how I could do it down here and its perpendicular distance would be 4 as well, okay? 4 feet. And then as I rotate this, this is also going clockwise, so that's going to be another negative. Okay. So go ahead and multiply and then add each one of these negatives together. So you should end up with a negative 94.47. What are my units? Kips times feet. Awesome. Yep. Don't forget your units. Kips times feet. There we go. That's the moment around A. Any questions at all? The big thing here is just going to be perpendicular distances and the direction of the rotation. Okay, that's going to be the practice that you'll get. We have to do one more moment around point D. Moment around point D. So if we go up here, we've got a new point now that we're going to put our finger on. Okay, so as we work around here, I'm going to put my finger on D. I'm going to rotate in the direction of, maybe I'll go this way. And I will pull in the direction of F3. It causes a rotation. And if I look here and I kind of bring this down, perpendicular distance is going to be 5 feet. So we're going to start our parentheses with 5 kips times 5 feet. And then the direction of rotation is going to be positive or negative. Positive, because it's rotating counterclockwise. Good. 5 times 5 for that one. The next one that we have, I'm going to do the F2, the 8 kips. That's also going to cause rotation to D. This is going to be 8 kips times perpendicular distance. We can move it backwards along its line of action. Pull, right? And that's going to be 8 feet is its perpendicular distance. Pull in that direction, positive or negative rotation. Which way is it rotating? It's rotating counterclockwise. So it's going to be positive out front again. Then let's do our Y component. Our Y component causes rotation. Okay. Its offset distance perpendicular is 8 feet. That one's easier to see. So we're going to take 7.8087 kips times 8 feet. What is the sign out front? What is it? Positive again. Yes, it's a counterclockwise rotation. Good. And then we need our F1X. F1X, if I push, if I move it along its line of action, it's going to go right through D. No rotation here. No inclusion on the moment equation. All right, go ahead and sum up each one of these and determine what the moment around D is. you look in the book, you'll notice that 151.5, I got 151.4696, so 151.47 kip feet. Positive direction. Okay, any questions at all? Awesome. Okay. So then, why don't we take a break? I was kind of looking at the time. It's probably a good time to do that after this example, and I'll give you like, let's say a 15-minute break and then we'll be back. So, let me stop the recording.